hardware fabrication. Can we say that we have stepped into the era of commercialized quantum computing? And the answer is negative. My reason is because current quantum hardware suffers from high and inevitable system noise. And this system noise challenges the applicability of quantum hardware. So before we can use quantum hardware to solve any practical problems with potential advantages, we need to solve many fundamental issues. And one of these fundamental issues is developing efficient quantum certification protocols. For illustrative, let me make an example using the IBM Q quantum device. As shown in the screen, here is a IBM Q quantum device with 127 qubits. As we can see, the average signal gate error is relatively high, which is about 0.08. And assume like a user submit a quantum program with about 10 signal gates on these devices, the success probability of returning the correct state is below 50%. In other words, we can say that this device returns an unreliable answer to the user. So this motivates the significance of quantum system certification, as the user want to know whether the result returned by the quantum computer is correct or not. So I'd like to mention that designing efficient certification protocols are very important, where the relevant results can help us understand behaviors of large qubit noisy quantum devices. And it will also help us to design reliable quantum algorithms. And more importantly, it can guide us to fabricate next generation error-corrected quantum computers. So due to its importance, huge efforts have been made to develop efficient protocol certification protocols in past years. And this figure provides an overview of past results. As we can see, when we deal with small qubit quantum devices, we can directly use tomography-based methods. But things change to be different when we deal with large qubit quantum devices, because in this regime, tomography-based methods are not infeasible because their computational complexity generally exponentially scale with the number of qubits. So we must design some clever protocols and tasks to help us to understand the behavior of large qubit quantum devices. Here is a short summary of prior results about quantum certification in terms of tasks level. So there are two main parts. The first part is about quantum state risk reconstruction, where the main purpose is to capture full information of the quantum system, but may be computationally expensive. Typical examples in this class include quantum state tomography, quantum process tomography, and quantum gate set tomography. Another class is to predicting quantum state properties, which means that we don't need to capture the full information, but we just need to capture some partial information. This allows us to devise some efficient methods. Typical examples in this track include fidelity estimation, entanglement estimation, and maybe others like random benchmarking, Hamiltonian learning, and self-testing. Okay, from another angle, if we classify quantum certification protocols in terms of the methods, we can also get two classes. The one class is non-deep learning approach, which has good theory, but maybe require extensive quantum resources. Another one is deep learning based approach, which is much more experimental friendly, which means that we just need to use few quantum resources to get the result we desired. But deep learning approach generally lacks of rigorous theoretical guarantees. So based on the aforementioned interpretation, we can say the tasks in quantum circuit certification is diverse. So we must to focus on specific one to develop relevant algorithms, which means that it's very hard to present a unified model to address all quantum certification tasks at the same time. So in this presentation, our focus is on the one of the most important certification tasks, which is cross-platform quantum circuit verification. The intuition of the quantum platform verification is shown in the below figure. As we can say, if a user doesn't know whether the result returned by a device is right or not. So a simple way is the user can submit the same program to two devices and verify whether both devices prepared the same state. So this is the basic knowledge or basic intuition of cross-platform verification. Note that these two devices can be arbitrary. It can be any quantum platforms like superconducting, photonic, ion trap, or one of these processors can even be classical simulator or some theoretical results. But in the later case, the cross-platform fidelity or platform verification task reduced to the direct fidelity estimation problem. So in this talk, our main focus is on the two devices are both quantum processors, and how to verify the output by these two devices. A general idea is measure their similarity, and based on this idea, the previous studies propose a concept named cross-platform fidelity, which measures the output of two devices. And we can see the formal definition of cross-platform fidelity is in this equation. The nominator just measures the similarity of the states rho I and rho j, which are returned by the device qi and qj when running on the same circuit U. And the denominator contains two terms. It just the purity of state rho I and the purity of state rho j. In the ideal case, we know that if the system is noiseless, when they run the same circuit, the output state must be identical, which means that the cross-platform fidelity is equal to 1. But in practice, due to the system noise, these two devices have different noise levels. So the prepared state rho I and rho j may be different, which means that the cross-platform fidelity will be less than 1. So here is a basic idea of cross-platform fidelity, and prior studies generally use random measurement or classical shadow to estimate the cross-platform fidelity. The basic idea consists of 3 steps. In the first step, the user just load the test circuit way to two quantum devices, and the different devices just transpile the circuit way using their native gates. And in the second step, the different devices just use random measurements, particularly poly-based classical shadow, to get some measurement results. And in the third step, these collected measurement results are sent to a classical data center with post-processing. Roughly speaking, they just need to calculate the reconstructed classical shadow state and estimate the cross-platform fidelity. But here is the weakness of using poly-based classical shadow to estimate the cross-platform fidelity. A key reason is that poly-based classical shadow is good at estimating local properties of quantum state, but the fidelity is a global property. So as we can say, the computational complexity to use classical shadow to get the cross-platform fidelity scales there is exponentially scaling of using classical shadow methods. So we must design some much more efficient methods to allow us to estimate the cross-platform fidelity on large qubit devices. Here is a key insight why we need to use deep learning to solve this issue. This is because we know prior test circuits can generally provide valuable information, which can help us to estimating cross-platform fidelity for the newly tested circuit. For example, as we know, in near-term quantum devices, we generally use hardware-efficient ansatz to run different quantum algorithms, and this hardware ansatz share highly structured layouts, and they can deliver some useful information. For example, if two test circuits U theta and U theta prime just have different rotation angles, but they have exactly the same circuit layout, we can expect that their cross-platform fidelity will be the same. This is an intuition of why we can leverage prior information to help us to reduce the measurement cost. But unfortunately, prior classical-based method cannot utilize this valuable knowledge to reduce the measurement cost. But deep learning or deep neural networks can capture this knowledge, and in turn, we can reduce the measurement cost or computational complexity for testing the new circuit. So the basic conceptual framework is as follows. Previously, we just use quantum state tomography or shadow tomography to get an estimation of the state rho I and rho J and the complete estimation. But when we use deep learning, we want to feed the measurement results or some output information of device QI and QJ using a neural network, and the neural network will distill some useful knowledge and map the input to a high-dimensional space, and then the output high-dimensional representation VI and VJ can give us a more accurate estimation of the cross-platform fidelity. So when we use deep learning, a basic or a direct idea is just to use prior deep learning approach in quantum state property prediction, which means that it undergoes a supervised learning framework. We just need to use the measurement data as a data feature, and we train a neural network to minimize its prediction with the ground truth. And after training, we get a trained neural network, and this trained neural network can be used to predict the cross-platform fidelity of the new test circuit. But this pipeline has some drawbacks, because from the perspective of AI, we know we are currently stepping into a new era, which is called the AI foundation models or large language models. In this era, we know when a learning model can get multimodal data, it can generally get better performance. This is like a human. Human perceives the world using vision, sound, and taste, and we can learn the world very well. So this motivates us to rethink how to design an efficient learning model for quantum cross-platform fidelity estimation using the idea of multimodal learning. There are two challenges to achieve this task. The first one is how to construct the multimodal data set, which can be used to solve our task. And the second one is how to design the corresponding learning model that can distill useful information from multimodal data set and enhance the learning performance. So our key contribution is solving these two challenges. And the basic framework of our model is shown in this figure. And we call our model as measurement circuit-driven neural network. And our model generally consists of 3 steps. In the first steps, we collect the multimodal data set. And in the second step, we implement our model. And in the third step, we optimize our model. In the following, for ease of understanding, we just call this measurement circuit-driven neural network as MACNet. So let us go in deep into each step. In the first step, we complete the multimodal dataset construction. And how can we construct this dataset? As we can see, this dataset contains in total capital S training examples, and for each training example, it contains 3 elements: XIS, JS, and FIJS. And the meaning of SIS or FJS is a data feature of state ROIS or ROJS, which means that the ROIS or ROJS means they are the prepared state of test accurate US on the device QI and QG respectively. And the data feature XIS or FJS contains 2 modalities, which are the measurement information and the circuit information. And we write down XIS as a combination of these two modalities data. And for the measurement information, XIMS, we collect this measurement information using poly-based classical shadow with M shorts. So how can we transform this data format to the one can be processed by neural networks? Here is the 4 steps. The first 3 steps follows the classical shadow. The first 2 steps follow the procedure of classical shadow. We just to take random measurements and record the measurement result in the classical memory. But in the third step, we need to flatten the local shadow to a vector, 8-dimensional vector. This is because neural network is good at processing real-valued data, but the local classical shadow is a complex valued matrix with a size 2 times 2. So we need to flatten them and take the map the imaginary part to the real-valued one. And we repeat this process with M times because we take M shots and we can get the measurement information with the size M times 8 times N. As for the circuit information, we just follow the idea of graph neural network or graph learning. We map the circuit layout after the translation to a DAG model associated with the additional information like gate type, noise, pivot index, and node index, and we store them as circuit information. And for the notation Fij, it just means the label of data, which refers to the cross-platform fidelity between the states ROI and ROG. When the multimodal dataset is prepared, we can implement our multimodal to train this dataset. And our proposed MACNet consists of 3 ingredients, which is the measurement branch, circuit branch, and the modality fusion operation. Now I will introduce the basic structures of measurement branch, which can be also called the measurement net. This branch only receives the data feature of measurement information, and when we have measurement data, it passes through several 1D convolutional blocks, followed by a pooling operation and a multi-layer perceptron, and then we can get a measurement feature. The reason why we adopt the pooling operation is because we introduce some inductive bias of the neural network, because we want to make sure that the output of the prediction of the neural network cannot be affected by the different orders of the measurements. So as for the circuit net, which is also called circuit branch, we just feed the circuit information to several graph convolutional layers, followed by the pooling operation and a multi-layer perceptron, and then we can get a circuit feature with dimension capital D. And in the last component, we just need to merge these two features in a high-dimensional representation. There are many choices to for the future operations. So in the literature of multimodal learning, we can use a direct sum operation, which means that we can map the measurement feature and the circulation use a sum operation, or we can also use a concate operation. Another one is pooling operation. But after the ambulation study, we find that attention-based fusion can generally get better performance. So we choose attention-based fusion as the fusion operation in MagNet. And the last step is to optimize MagNet using the collected multimodal data set introduced in step 1. So the optimization contains 2 steps. In the first stage, we need to independently training each branch, which means that when we're training the measurement branch, we need to frozen the weights of the circuit net. And similarly, if we want to train the circuit branch, we need to frozen the weights of a measurement branch. And after this stage, we go to the second stage. And in this stage, we need to train both the weights of measurement branch and the circuit branch at the same time. And the object function to guide the optimization is defined in this equation. As we can see, it's just a mean square error loss. And the capital S means the total number of training data, and the function D is the per sample loss, just like the mean square error. And the F hat is a predict cross-platform fidelity result of our model. And the definition is showing here. As we can see, the nominator is the inner product of the representation learned by the neural network. And the denominator contains 2L2 norms to avoid, to introduce some regularization. Okay, now I will introduce some numerical simulation results of our proposal. And in the first task, we want to certify 6 qubit quantum devices. And the data set construction as follows. We just to use the hardware equation ansatz with different layout, which means that the entanglement gate can be arbitrarily connected between any pair of qubits. And the rotation angle theta can be randomly generalized. And use this method, we can get a training set with a size of 1,000 and 500. And for the 2 devices, we apply different local depolarization noise channels with different polarization level. And we set the short number of class shadow as m equals to 500. And here is a combination of the original method, which means that the classical based method, and solely trained on measurement net, circuit net, and MagNet. As we can see, for classical shadow, the predict or the estimate cross-platform fidelity has a huge gap to the true result. And for the measurement net, it gets a much better result. As we can see, the predicted value is very near to the ground truth. But the best performance is the MagNet. When we combine the multimodal information, it gets best coefficient of determination. And this also, by comparing the second figure and the third figure, we can know that the modality of circuit and measurement provide complementary information for the learning. This is why MagNet can achieve the best performance than solely trained by circuit net or measurement net. Here is another comparison based on the metric of mean square error. As we can see, MagNet also achieves the best performance. In the next, we explore a large qubit case where we use our model to certify 30 qubit quantum devices and 50 qubit quantum devices. The data set setting follows the prior task. But except for increasing the total number to 500 in the case of 30 qubits and m equals to 20,000 for the case of 50 qubits. But in both cases, we can see the magnet achieves good performance. Its prediction is very close to the targeted result, and the coefficient of differentiation is very close to the ideal number 1. And in the task 3, we consider a more challenged noise model. Instead of the depolarization noise model, we consider the noise model from IBM Q device. And here is the simulation result is shown here. The figure A shows the prediction result compared to the quantum tomography. As we can see, for devices, the prediction of magnet is very close to using the quantum tomography. But one thing you need to note that magnet use very few measurements compared to the quantum tomography. And figure B shows the feature learned by the magnet before the training and after training. The hollow markers refer to the high dimensional representation before the training. As we can see, there is no general rules, and it's scattered randomly. But after training, we can say it learns good representations because the notation A, B, C, G refer to 4 quantum devices, and we can clearly see the quantum state from different devices cluster somewhere. Okay, I like to give some outlook and a discussion about our work, and we know our key contribution is introducing the system information into the quantum in the data-centric quantum learning. Different from prior studies, just use the measurement data to train a learning model. We explore how to introduce much more prior information in the data set and in the learning model to enhance the learning performance. And this paradigm can inspire us to devise or develop more clever or efficient methods. From the system information level, we need to think how to devise other efficient strategies to store or compute measurement and circuit modalities. This is because we know that even we use classical shadow to store data, when we deal with quantum qubit larger than 100 qubit, we still encounter the memory issue, especially when the total number is set like more than 10,000. And another issue we need to think is how to develop the novel transformation methods to map the original formats to those that can be processed by neural networks. In this work, we use the flatten method, and for the measurement data, and we use the DAG graph of the circuit information. But this is not unique. Maybe we need to think some other efficient ways to further improve the learning model's performance. And another way deserve to be further explored is discovering other modalities beyond the measurement data and the circuit information. But currently, we didn't find any other useful information or generic information can be easily injected into the learning model. And from the task level, we need to think how to apply our protocol or its variants to address other quantum certification tasks. So typical examples include similarity testing, state correlation prediction, or maybe we can think how to use it to predict like analog quantum simulators like ground state properties or maybe others. And another way we need to think is how to build a unified data set to address different quantum certification tasks at the same time. A recent work from Hong Kong University considers how to devise a learning model for multitask learning. but I think this is just an initial work, and we need to explore more interesting results. Okay, thanks for listening.